All right, so welcome back. Today we're going to continue with, or we're going to conclude actually with conditionals. You had some pretty good practice in your labs on yesterday, and you'll get some more practice with conditionals with your hack tomorrow. We're just going to finish up today with some of the loose ends though, and maybe also do an exercise similar to what you did yesterday in your lab. But we left it off on whatever it was, Wednesday of last week, so over a week ago now, with a couple of pitfalls. So the first pitfall that we saw was that you can do ranges, but you actually have to split them up into two conditionals using the logical AND here. The reason that this didn't work is it compiled, it ran, but it didn't give the correct results because of how it is evaluated. If A were, say, 15, right? Then 0 is less than or equal to 15 evaluates to true. And what's true in C? 1. So this ends up being 1, and then 1 is less than or equal to 10. That's still true, right? So it gave us the wrong results. The second pitfall is the following piece of code. And let's go ahead and take a look at what it does. So here I'll go ahead and compile it. Demo. Oh, there we go. Come on. There we go. And run it. Now A has been set to 10, and we're checking to see if it's 5, and if it is 5, then we print it out. At least that's our intention, right? And it prints out that it is 5. So what's going on here? What's wrong? Visually, what's wrong? There's a single equal sign here. Is the single equal sign used to test equality? No. Two equal signs are used to test equality. So the correct piece of code would be this with two equal signs. And when we run it now, of course, we don't get that print message anymore. Now, I'm going to roll this back. Remember the tool that I showed you briefly on Wednesday to how to avoid this? What was it called? The wall flag, right? Or it's basically what's called a linter. So if I compile this with the wall flag, it would have detected this and reported, hey, something looks wrong there, right? It's not an error, right? It's not bad code. It's syntactically correct. But there is a warning. There's something going on here. I don't necessarily think that this is what you meant. It is lint, right? It's not dirt on your clothes. It's just lint that you can pick off. Double check to see if that should be there or not. It's not dirt. I don't know what it is. Please check it. Give it a second look, all right? So again, using a linter, using the wall flag, will really help you to discover these errors. So again, the mistake is using a single equal sign, the assignment operator, instead of the equals equals equality operator, right? Remember to always, and we'll talk a little bit more formally here about what a linter is in a moment. Let's consider the another pitfall here. In fact, we saw this pitfall on Piazza. So consider the following piece of code, where I've got, if A is equal to 10, then we print out that it's 10. So what I'm going to do is I'm going to take this over, and let's go ahead and cut and paste it there, right? Bad style, bad indentation, but how can we fix that? What's the other tool? A style, right? Or we can get into the habit of writing it correctly the first time, and then we don't have to worry about that, right? You wouldn't start out an English paper with just a mash of words, no spaces, no periods, right? You'd actually write an essay how you intend at least a little bit of the formatting of what you intend the final product to be. Likewise, 90% of the problems that we saw over the weekend or yesterday with the lab was everybody's white space was all over the place. They couldn't find the opening curly bracket and closing curly bracket if their life depended on it, because everything was everywhere. If you have good style, it's really easy to see, oh, I'm missing a closing bracket because it's not aligned, right? Make sure that you have good style up front. Don't rely on tools like A style, all right? All right, so is this going to print A is equal to 10 or not, if I save it? Let's find out. Oops. Ignore that for a second. There. I'm going to compile it without that wall flag, right? Bad idea. Because when I run it, in this case, it's going to work. right? A is in fact 10 because I set it to 10. Let's set it equal to something else. 5. Should it print out that A is 10? No, but it does. Why? Let's ask our wall tag. Right? This statement, oh, go ahead. What's wrong? Yeah, the if clause does not guard. You know, okay, what does that mean? Well, it's not all that helpful to a beginner, to beginning programmers, but at least it highlights that there's something wrong with line 13, right? If A is equal to 10, then do what? Let me go ahead and rearrange the code here so that it's clear of what it's doing. What is it doing on this line? Nothing. If A is equal to 10, do nothing. Then move on with the rest of the program. By writing it like this with a semicolon, remember semicolons end executable statements. An executable statement can be empty. Right? So what this is doing is this is saying if A is equal to 10, do nothing, end the executable statement, and then move on. Right? It is not binding this if statement to this block right here as our intention should be. Right? So let me go ahead and fix that by getting rid of that semicolon. And we'll see now that it's no longer going to complain about that line, and it actually runs correctly now. Okay? So be careful. Make sure that you're using the semicolon properly, and make sure that you're using the wall flag always. Right? So a little bit up on the wall flag here. I'll just go ahead and copy this over and remind you what a linter is. Here we go. So code can be syntactically correct, meaning that it'll compile. The compiler is saying there's nothing wrong with this code. It conforms to the syntax. It's like reading your English paper and saying, oh, the spell checker says there's nothing's misspelled. The spell checker says that every sentence ends with a period. Right? Does that mean that it's a coherent essay? Not necessarily. Right? Instead, there might just still be some issues in there that need to be checked. And so a linter is what's called a static analyzer. Static analysis tools simply mean that it's going to look at your program before it compiles. There are dynamic analysis tools that we'll check out later, debuggers, profilers, and stuff like that, that analyze your code, analyze your program after it's been compiled. Static analysis tools look at it before it even goes to compiling. It looks at it and says, you know what, that looks fishy. Did you mean to do that? Because you can do that if you really want to, but I don't think you meant to do that, right? Using GCC as a linter is really easy. All you have to do is use the wall flag. And again, what that stands for is hyphen warnings, capital W, give them all to me. That's not the wall flag like a wall, but that's what we call it. It's warnings, turn them all on so that you're telling me what's going on. It is vitally important that you pay attention to that because we run the grader with the wall flag on, and so all warnings have been turned on, and you have to address all warnings. We saw a lot of labs yesterday with a whole bunch of warnings, and those warnings were directly related to bugs in programs. If those warnings had been taken care of, then your programs probably would have been correct, right, in a lot of instances. It's best practice to always compile with all the warnings on, especially when you're a beginner and beginning out and starting C, so that you that you look at all and see and at least notice all these problems. And again, it's just lint. It might not be a bug. It might be, you know, no, I meant for that to happen because of various reasons that maybe you can come up with, right? But at least you're taking a second look and saying, yes, I did mean to do that, okay? Very rarely did you mean to do that, though, right? Warnings are very, very useful, okay? All right, there's another thing that you should be aware of called short-circuiting. Let's see, yeah. So let me go ahead and go into here, short-circuiting. Because it's what's called an idiom, a programming idiom. And I'll get to what that means here in a second. So consider the following logical statement. Suppose that A and B are Boolean variables, in other words, integers, 0 and 1. We've got A and B, right? Suppose that A evaluates to false. Does it matter what the value of B is? No, why? The logical and statement, it's also called conjunction. Logical and statement is true when both of them are true. If the first one turns out to be false, 0, does it matter that this is true or false?
So there's no point in evaluating B.
Exactly. There's no point in evaluating B, and so it doesn't. No matter the value of B, the statement is false. Right? Consequently, C does not, and C and the vast majority of languages do not even look at B or evaluate it. Now, if it was some complex expression, like say a function call or an entire, like a whole bunch of numbers that you multiply together or something like that, it won't do it. And the reason for this is you have to think about historical context here. Go back 40 or 50 years. If you have a computer that operates on the scale of, a few operations per second, and you can cut out a few extraneous unnecessary operations, you absolutely did it. Because then that adds up. That's seconds of computation time 40, 50 years ago. Nowadays, it doesn't really matter, right? It's that kind of optimization, who cares? Because we can do millions, billions, even trillions of operations per second. But it's still necessary. It's still part of most languages because it's come to be expected, right? But understand that it was done this way to save computation time, to save CPU cycles. And so if you can get by cutting out a few extraneous operations, you did it, right? And consequently, all programming languages do this. It's called short-circuiting. Why is it called short-circuiting? Think of the evaluation as a circuit. Everybody knows what a circuit is. You go from a power source to, say, a lamp. It lights up the lamp, but you have to have a circuit because current, electricity flows in a circuit. It goes from the power source to the lamp, lights it up, and then it flows back, right? It's always in this circuit. Now suppose that we put something in between that circuit. So here's the circuit, and I short circuit it by putting a wire across it. Does the power source get to the lamp anymore? Nope. It travels to the path of least resistance. You've short-circuited the circuit. You've shorted the circuit, right? And if you did it with, say, a raw wire, then you could have sparks everywhere, right? Or if you did it with a capacitor and you release the built-up power, then you get a nice spark show, right? So that's what's called short-circuiting. In code, you're short-circuiting the evaluation. You want to evaluate A and then B. But if you evaluate A in a logical AND statement here, then there's no reason to even look at B. So instead of going over to B to look at it, you short-circuit it and immediately say this entire thing is false. Right? The same thing happens with a logical OR. So consider the following: A or B. Now in this case, if A is false, is true, does it matter what B is? A or B? A is true. Does it matter if B is false or true? The first one is true, therefore the entire thing is true, right? So no. Again, it is short-circuited and not evaluated, looked at. So consequently, you get away with a few CPU cycles. Nowadays it doesn't matter, but the optimization is still there because it's come to be an idiom. It's come to be expected. So this is a common programming idiom. It's why all languages, except for maybe one or two languages that I don't even remember what they are, all languages support this. Any language that you're going to encounter probably in your lifetime will support short-circuiting, will use short-circuiting. And it's a common programming language idiom. What is an idiom? Right? I often, draw parallels to programming and writing an essay, programming and writing a bunch of, like even prose or whatever. What's an idiom in the regular English language? No? All right, yeah, go ahead.
A phrase that most everyone knows.
A phrase that most everyone knows. That's great. Or as Archer called it, a colloquial metaphor, right? It's a metaphor that everybody knows that's in that culture, right? So, for example, it's raining, it's not, it hasn't rained in a while, but it's raining cats and dogs. Think about the literal interpretation of that. Think about taking that phrase and translating it to another language where they don't have that idiom, they don't have that metaphor. Is it going to make any sense to them whatsoever? No. Take every language has idioms, by the way. Take an idiom in another language, translate it to English, and we would be like, what? What the hell does that mean, right? You have to transliterate it. You have to translate not just the words, but the actual metaphor. This is a metaphor. This is something that you have to understand once you're in that culture. Once you've learned the language and you pick up these idioms as they go, as you go along and learn the language. Just like somebody learning English for the first time, or us learning a foreign language for the first time, you hear this idiom and you go, what the heck does that mean? But once you've been explained the meaning of the metaphor and the context, then, oh, okay, now I understand that. Now I'm part of that idiom. It's become part of my shared culture, shared understanding of that language. So this is one of those idioms. Understand what short-circuiting is, and that it's there. And eventually you'll have to use it too, okay? There's stuff like that all over the place with programming languages, okay? Okay, let's see. Let's do one quick exercise before we move on to the next topic here. All right. This exercise is going to be very, very similar to what you did yesterday with the taxes. That given a range of stuff, you have to describe what that range is. You had to compute taxes yesterday. In this case, we're describing the decibel levels. The decibel levels of, say, the Husker game last Saturday. If the decibel is 0 to 60, it's kind of quiet. If the decibel level is 61 to 70, it's conversational. Then it gets a little bit louder. Then it gets dangerous, and there is such thing as a lethal decibel level. A decibel is nothing more than a compression wave, right? So if you've got an explosion, that there's a decibel level associated with that, right? You cannot have negative decibel levels because, again, it's pressure differences in an atmosphere. And so you can't have something like -5 decibels. It's not like noise-canceling headphones. There, the amplitudes of the sound waves are canceled out, right, by flipping them. Okay. So let's write a program to do this. First step is we need the input. So do we want to do this with command line arguments to get more practice there, or do we want to do this interactively? We'll prompt them for the input, and then we'll use scanf to read it in. Which one do we want to do? Command line? Okay. So I'm going to go ahead and use conditionals to check to see if they gave me enough command line arguments. How many arguments should I expect? Remember, argc is argument count. If that's not equal to 1 argument, then print error, give me your decibel level, right? And then we'll go ahead and exit on them. Don't worry about that 1 there. Should we be expecting 1 command line argument? 2. Why 2? The first one is always the executable file name. Then the decibel level after that, right? So let's go ahead and do this piecemeal. And what we'll do is we'll echo it back to them. We'll print out you entered, printf, or printf, decibel level, and we'll print it out. What kind of, I guess we have to read it, right? So decibel is equal to, how do I convert it, the command line argument, the first user provided one, how do I convert it to a number? A to I or A to F. Which one do we want, A to I or A to F? All right, and, that means that we're going to assume that the decibel level is an integer, right? Without any other specification over here, that's a good assumption. But what's one consequence of that? How many people went to the Husker game? They usually, when they're trying to screw up the audibles or whatever, right? They get louder, and then they print the decibel level, whether or not it's real or not. Is it an integer? No, okay. What was it like? Let's see, loud. 108.4. Did it get up to? I don't know. What was the record decibel level on Saturday? Who knows, right? But you would have an argument either way, right? in this description, we only gave integers, so maybe implicitly we only meant integers. But maybe 60.5, I know something about decibels, and so I'd say, well, you can have 60.5 decibels, but is that quiet or is that conversational? This specification here is incomplete. And if you ever face this in real life, you would go back to the person that wanted you to write this program, the stakeholder or whatever, and you would have to elicit feedback. Well, is it okay, or do you want to support decibel levels of, say, 60.5? Oh, yeah, I guess I didn't think about that when I wrote this up, right? And then you would get that feedback. What happens when the decibel level is negative? What happens when the decibel level is more than 195, right? What happens when it's between these two, right? And you'd have to go back and forth. That's called requirements elicitation or specification gathering, a bunch of different fancy words for it. Basically, you have to ask somebody to clarify. What did you mean in this case? Because I can't program it. Or, you can assume, oh, okay, they must have meant integers. It's on them because they didn't give me enough specifications. I will go ahead and argue that it conforms to what you gave me. Here you go, we're done. Move on. And by the way, I'm going to charge you double to come back and fix it if you wanted different specifications. You should have been more complete with your specifications. Sorry about that. Right? It all depends on whether or not you are dictating the price and terms. So what do we want to do? Do we want to do integers or doubles? Double? Okay. I'm okay with that. There we go. And to print the double, it would be %f, decibel. There we go. Let's go ahead and see if it works. I'm going to compile with the wall flag. No warnings. Great. Give me your decibel level. All right. 10. Right? And it looks like it's good to me. Of course, make it prettier by going to the next line. All right? Okay. Now let's take care of the actual program. I want to take care of whether or not it's quiet. So how can I write that? If the decibel level is between 0 and 60, all right? So 0 is less than or equal to decibel less than or equal to 60. Is that correct? Nope. What's that going to happen here? It's quiet. Yeah, what's going to happen? It's always going to print this no matter what. And again, if I use the wall flag like I should, it's going to warn me of that. I need to split it up. If the decibel level is greater than or equal to 0, and the decibel level falls below or equal to 60, then we'll go ahead and say it's quiet. Okay? Let's just go ahead and test it really quick. Of course, it's not a fair test to test something that is not quiet, so I'll just go ahead and test quiet for now. 10, it's quiet. All right. Do I need an apostrophe there or not? I don't know that much English, so. Apostrophe it is quiet. I think I need it, but okay, whatever. Right? It wasn't in the specifications. Else if. Now let's take care of the second conversational, 61 to 70. All right? Else if 61 is less than or equal to decibel, and decibel is less than or equal to, what was it, 70? Yeah, 70. Conversational. Printf, it is conversational. Right? Avoid that apostrophe issue altogether by writing it out. Right? And let's go ahead and test for this. So compile it, run it, and let's do something that's quiet, 65, or conversational, excuse me, and that works too. Yeah, go ahead.
Since we have the doubles in this, shouldn't we put it to 60 without the equals?
That's a good question. What happens when we go with something intermediate, 60.5? It doesn't print anything, right? In fact, let's go ahead and put in an else, printf, unknown level, right? That else will catch that possibility now, right? 60.5, unknown level. But is it? I don't know. Not that. Is it quiet or is it conversational? Again, it's a bad specification. Maybe, do we want to err on the side of quiet or conversational? Which one? Conversational, okay. Because we go from 0 to 60, anything above that and up to and including 70, we'll go ahead and consider that to be conversational. So I'll go ahead and change this to if it is greater than 60, right? Strictly greater than. Why? Does this make sense? What if it's exactly 60? It's both quiet and conversational? Say what? Okay, so we've got to vote for it'll just run quiet. Let's find out what it is at 60. And you're right. Why are you right, though? Remember how an if-else statement works? The first one that evaluates to true is the one and only one that gets executed. They are all mutually exclusive. If you've got 4 statements, only one of those 4 is going to execute, as long as you've got an else statement. So, I'll be explicit about it, though, and I'll go ahead and make sure that it's a strictly less than. All right. Before we continue, though, is there an optimization here that I could probably consider? Yeah. Yeah, I don't need that first one at all. Why? How did I get to this point? How did I get to line 24? It was already over 60, right? So do I need to check for it's over 60 explicitly? No. Otherwise, I wouldn't even be here, right? So I can simplify that and get by with only one check, right? Simpler code, shorter code, is more readable code, is more understandable code, okay? Else if, and let's go ahead and use that same pattern throughout. Decibel is less than or equal to, what was the next one? 110. That's going to be loud. Printf, loud. Oh, did I misspell conversational? Or what did I spell? Decibel, thank you. There we go. Else if, and then what's the last one? 194. If it's decibel is less than or equal to 194, then it is dangerous. Danger. There we go. And then else. Did I take care of them all? Okay. Maybe, maybe not. Let's go ahead and test a few things. What if it's 195? Oops. Sorry. 195 should be unknown, right? Because that was not part of the specifications. 190, however, is dangerous. Give me something else to test. Oh, minus 10. Predict. It should be unknown, right? So, predict what's going to happen. Conversational. Why? So, is negative 10 between 0 and 60? Nope. Keep going. Is negative 10 less than 70? Less than or equal to 70? Yes. And so consequently, this gets executed. So let's rethink this and take care of the error condition first. If the decibel level, decibel, is less than 0, then we'll go ahead and printf invalid decibel level. Because it's not just unknown, it's invalid. There's no such thing as a negative decibel level. Right? And now I can go ahead and put an else statement, else if statement here, and I can use the same simplification as before. It would be greater than or equal to 0 if I got to this point. Right? Cool. And of course, now I need to go back and test everything again. Oops. There we go. And run it with negative 10. Okay, invalid decibel level. Run it with 10. Run it with 20. Run it with 195. Do this over and over and over again for all those tests that I designed. Or I could do what you did in lab yesterday, right? Where we gave you a test suite for the leap year stuff, and then we told you to add on to it. That's automated testing. It's still kind of informal unit, what's called unit testing, but at least we're headed in that direction. You're going to be exposed to a formal unit testing framework in Hacks 5 and 6, okay? Where you don't have to write all that boilerplate stuff over and over and over again. This passed, great, add 1 to the number of pass tests. This failed, add 1 to the number of failed tests. Report everything at the bottom, right? Instead, you'll use a more formal testing framework where you don't have to write all that boilerplate code, okay? All right, I will make sure that you have this in your notes. And again, that's posted to GitHub when I get home. There we go. There's the program. Okay. All right, any questions on conditionals? No? Okay. We have plenty of time then, so let's go ahead. I'm going to go ahead and get rid of this. And let's go ahead and start on the next topic here. So conditionals are the basic control structure that allows you to make decisions, A or B. The other kind of control structure that allows you to do nonlinear control flow is loops. So whereas, usually you have sequential control flow, if you've got a statement A, B, C, it goes A, B, C. Conditional says, okay, well, wait a second, we have a decision to make here. Do we do A or do we do B? Or do we do A or not A, if it's just an if statement? Loops allow you to take a piece of code and not just have to make a decision, but repeat it over and over and over again as many times as you want. Of course, do you want to repeat this forever? No, that's called an infinite loop. Sometimes you do want infinite loops. They're called pull loops. For example, my computer is sitting here in a pull loop right now, waiting for me to move the trackpad or to type or something. It's sitting there constantly saying, do you have any input for me? Do you have any input for me? Do you have any input for me? Until I hit the switch and shut it off, right? So sometimes you do want infinite loops. Not very often, though. But we do need a way to repeat pieces of code. If you've got a chunk of code that needs to be repeated multiple times, you don't just take the code, cut, paste, cut, paste, cut, paste, because first of all, you're hard coding how many times it executes, but also you're cutting and pasting. We call that copy pasta, right? Now, a lot of people have called that copy pasta in, say, online forums where they just copy something and then paste it. It started in computer science first, by the way. So they stole it from us. Where copy pasta is you're just copying code over and over again. Put that stuff into a loop, right? Put that stuff into a loop and repeat it. Don't copy pasta, okay? There are 4 basic elements to a loop control structure. Every loop has a beginning. That's called an initialization statement. If I'm going to jump into this loop, if I'm going to jump onto this track and start running around, I have to start somewhere, right? The continuation condition tells me that I should keep going around that track, right? Nope, one more lap at least. Keep going, one more lap. Keep going, one more lap, right? You haven't hit your mile yet, or however big your track is. That's called a continuation condition, that you should continue until this is no longer true. Just opposite of that, if you negate a continuation condition, should I continue? Yes. Should I continue? Yes. Should I continue? No. That's a termination condition. No, you should not continue anymore. You should terminate this loop, take a rest. Right? Don't run around the track anymore. Now you have to make progress towards that termination condition. If you don't make progress towards the termination condition, you're just running around the track forever. Sometimes, again, you want that, but it's called an infinite loop. Right? And if you just keep going forever and ever and ever, making no progress towards that termination condition, then you're not going to get anywhere. Right? And finally, you have to be doing something. Right? A loop is useless if it's empty, just like an if statement is useless if it's empty. An else statement is useless if it's empty. So you actually have to be doing something within your loop, and that's called the loop body. Okay? So let's take a look at a really, really simple example. And to do this, I'm going to use what's called a for loop. Surprise, surprise, it uses the keyword for, right? Now, all 3 of those first conditions are on the same line. This is the initialization condition. Int I is equal to 1. Where do you start? I will start this, it's called an increment variable. I'm just calling it I. I is a terrible variable name to be in general. But if it's being used in a control structure of a loop like this, it's perfectly fine, because what else does it stand for? I don't know, right? So I'm going to start it at 1. That's my initialization statement. My continuation statement comes next. While I is less than or equal to 10, continue, right? Do one more lap. Lap 1, lap 2, lap 3, lap 4, all the way up to lap 10. Once you get there, then you can stop, right? I plus plus. Now this is new syntax that we'll talk about in a second here. For now, just understand that it's equivalent to setting I is equal to I plus 1. I'm just adding 1 to I. So I goes from 1, 2, 3, 4, 5. We call this syntactic sugar. Why do we call this syntactic sugar? First of all, what's sugar? Is it necessary? Nope. But is it? It's really nice, right? Yeah, we like sugar, right? We don't need it. Right? We can go without it. We can have a programming language without syntactic sugar, but it's a little bit better if we sweeten it up and put in some sugar, right? It's just like language. We don't need 50 different adjectives to describe cold, right? But it's nice to have them because they describe different levels of cold. It makes your language richer. It makes it nicer to speak that language. And so with coding, we like shortcuts like this. We like syntactic sugar. There are some languages that don't like syntactic sugar. Swift, for example, doesn't allow some of this. This I++ is not in Python, for example. Swift is another language that doesn't have what are called compound assignment operators. Why? Because we don't like sugar. We don't need sugar, right? So, all right, fine, whatever, right? But anyway, I like sugar. Mine's a sweet tooth. I prefer sugar to, say, fried foods and stuff like that, except for Chex Mix. Chex Mix and sugar. I'll eat those till, and donuts and all that stuff. Awesome, right? All right, so I starts at 1. It continues while I is still less than or equal to 10, and it goes up by 1 each time. Now inside this, we have a loop body, and because otherwise we would be doing nothing. And for this, I'm just going to simply print out the value of I so that it reports it. Right? Now, what is this going to ultimately print when I run this? Let's walk through it. I is going to start at 1. 1 is less than or equal to 10. That's true. So this loop executes and it prints 1. At the end of this loop, it will increment to 2. Now I is 2. I is still less than or equal to 10, so it still executes, and it prints out 2. It prints out 3, 4, 5, 6, 7, 8, 9, 10, right? 10 is less than or equal to 10, and so this will be printed out. But then what happens? 10 becomes 11, right? I don't have enough fingers to do that, sorry. Right? So is this going to print 11? Is 11 less than or equal to 10? No. At that point, you don't continue the loop. You break out of the loop and say print done. All right. Let's see it in action. Oops. There. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, done. What about after the loop? We said that 10 went up to 11, right? Let's print it out and see if that's in fact true. I is equal to %d and the line I. So if we were right and it went up to 11 after the loop, then it should print out 11, right? Let's find out. Doesn't even compile. What's the message here? I is undeclared. Wait a second, I declared it. It's right here, int I. Right? This is something called scoping. So what does scope mean in real life? If you look through a scope, can you see the entire world? No, what can you see? Only what you can see through the scope. A variable has scope. A variable only exists in some area that you look at, right? So in this case, the variable I, because I declared it inside this loop, as part of this loop, its scope is limited to the for loop. It exists at the beginning of this for loop. It exists on each iteration of this for loop. But after this for loop, it no longer exists. It goes out of scope, right? It only exists in that small scope that you're looking at for that particular for loop. Now, if I had done it differently, if I had done, say, int I, right? If I declared it up here, and then I didn't declare it here, and I set it equal to 1, less than or equal to 10, I++, now it does exist. It exists for the entire program. Now it compiles. And our prediction that it is, in fact, 11 is true. Right? That's because I changed the scope. It now exists from line 12 all the way down to the end of the program. Now, which one looks better? This one where the scope is as wide as possible, or the original where the scope is as limited as possible? Right? Limited. I like limited too. Why? Because it's more predictable. It only exists for this one segment where you need it. If you don't need it over here, then don't make it available over here, right? Only take, don't take, if you're going on a trip, you don't pack everything in the damn house, right? You only take what you need with you. Just like in programming, you make sure that you limit the scope of everything that you can as much as possible. If you have a need to widen the scope, then so be it. But you should always prefer limited scope as much as possible, okay? So let's go ahead and bring this over and note a for loop. Right? So the first type of loops that we're looking at are for loops. Right? The three main parts, the initialization, the continuation, and the increment, are all located on the same line. And here's the example that we just did. There we go. They're all on the same line. Note the other pieces of syntax here. I didn't just put willy-nilly semicolons wherever I wanted. Where are they? Semicolons are necessary on the first two, but not used on the second. Right? Or on the third, sorry. First two, but not the second. I've got a semicolon right here after the initialization condition. I've got a semicolon right here on the continuation condition, but I do not have a semicolon on the increment condition. Right? The body is surrounded by opening, closing curly brackets. No, you don't have to do that if you only have one statement like I have here. That's terrible practice. Forget what I just said. Always use curly brackets, no matter what. All right? So, but technically you don't need it in this case, but always use them. Okay? What else to note about this? Oh, the scope. In the above example, sorry, there we go. Let me give myself some more room here. There we go. Hopefully that'll snap too. In the above example, the scope of the increment variable, I, is limited to the loop itself. It exists in the loop and for each iteration of the loop, but not after the loop. Right? That's why we got that compiler error. It didn't know anything about I. If you've got multiple loops, here's loop 1, here's loop 2, here's loop 3, each one of them can have their own increment variable, and you can name it the same thing. Int I is equal to blah, 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 blah. Int I is equal to the same thing, right? It's okay to have multiple variables with the same name as long as you are limiting the scope of those variables to each one of those loops. Okay? Again, the I equals 1 is the initialization. It only executes once before the loop executes. The continuation condition was I is less than or equal to 10 and is checked at before the execution of each iteration. Right? If false, the loop ends or terminates. The continuation, or sorry, the increment statement is executed at the end of the loop. Right? That's why we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Imagine if I++ occurred at the beginning of the loop. We start at 1, and then we immediately increment to 2, then it would have printed something different, right? And so it's always done at the end. And again, there's no semicolon at the end. Another observation. or some other observations here. The increment automatically is executed at the end of the loop. The I++ syntax adds 1 to the variable I, right? You might imagine, how could we take away 1 from the variable I? I minus minus subtracts 1 from the variable I. And we can do that with any variable. You can go plus, plus, minus, minus. Alternatively, you could have written I is equal to I plus 1. Right? Alternatively, suppose that you wanted to go by a different increment. I don't want to go up by 1. I want to go up by 2s. I want to go 0, 2, 4, 6, 8. Right? I want to go up by 2s. You can do that using I is equal to I plus 1, or plus 2, excuse me. Or you can use a compound assignment operator. And in this case, it's I plus equals 2, right? So what this is doing is it's adding 2 to the variable I. You can change that to whatever you want. You can change that, some other examples here. You can change it to I plus equals 10 if you want to go up by increments of 10. 10, 20, 30, 40, 50, or whatever you started out with. You can also use other expressions. So if I plus equals A, right? This adds whatever is stored in the variable A to I, right? It's equivalent to, say, I is equal to I plus A, right? And that's what, again, it's syntactic sugar. It's a way of writing something a little bit shorter, ever so shorter. It's not that big of a savings. What do you get out of it? You get out of not having to write I again. Oh, okay, big deal. Yeah?
Does this also work for multiplication and division?
Yes, it does. It works with plus, minus, multiplication, and division. So again, for example, A or I times equals 2 would multiplies I by 2. Oops, not 21, 2. Another example, I divide by equals 2 divides I by 2. Except, careful, what if I was 5? 5 divided by 2 is what? 2.5, but what happens with integers in programming? Truncation. So it results in truncation. 5 divided by 2 would end up as 2. So be careful. So take care with truncation. And again, that's only for integers. Okay? And finally, go out one here, by declaring I within the loop control structure, we limit its scope, right? The area of the code in which the variable exists or is visible, right? It actually may or may not, whatever the machine code happens at the machine code level, I don't know. It optimizes a bunch of stuff, we'll never know. But as far as the high level C code goes, it doesn't exist after the loop, okay? All right. Yeah, in fact, I don't know, let me try something really quick here. STD equals C89. Yep, there we go. Okay. So 89, how many years ago is that now? 32 years ago. 32 years ago, you could not write the code that I just wrote. Right? You could not scope a variable to a for loop, to inside of a for loop. You had to write something like this, right? Now, it used to be that the CSE was set up, and if you are working on CSE, this may be a problem, but if you're working on the CS50 IDE here, you're okay, and you could ignore me for the next minute. But basically, 32 years ago, the standard of C, that's what I just did here. I compiled it for 1989 standards. And in 1989, you were not allowed to create a variable like this. Only in 1999 did they update the standard so that you could do something like that. But 10 years prior, they did not allow you to have a loop scoped variable like this. In fact, I can't do it here because I don't think it goes all the way back to the ANSI standard. Oops, ANSI. 1979. In 1979, all your variables had to be at the top. You couldn't have variables at the bottom or somewhere inside of your program. You had to move them all the way to the top because the compiler writers were lazy. Right? They didn't want to write sophisticated code that allowed you to do whatever you wanted, wherever you wanted. So you do have to understand that, that there are different standards out there. And if you're ever stuck with an old school standard, then, oh well, you'll have to restructure your code a little bit. But you don't have to worry about that anymore because I think that the standard here, I think it's on 2011 at least. That's 10 years ago. And is there a 21? Not yet. Right? So it's been updated about every 10 years. We do not like updates. Updates break things, right? The C language is very, very conservative on that front. They don't, in fact, going from one standard to the next standard, only very few tweaks were actually introduced into the language. You could pretty much still compile most code written 30, 40 years ago today with very, very little changes. Because we like that. We don't like a lot of changes because we don't like our code breaking. Contrast that with a programming language like, say, JavaScript that changes every other damn week, right? It's hard to keep up. Every change is a breaking change, and we don't like that, right? Some people like that, but whatever. Right? Okay, so the default standard is what you'll want to end up using. You don't have to provide a flag at all. Again, now you can stop ignoring me if you don't care about it, okay? All right. Let's see, what else? One more type of loop here, and then we'll go ahead and pick it up on Monday. The other type of while loop that I'm going to show you is a while loop, right? While loops have slightly different syntax. First of all, they use a different word. So for loops use the keyword for. What do you think while loops use? While, right? Wow, surprising, right? So let me go ahead and write the same loop here, but as a while loop. While I is less than or equal to 10, I will go ahead and print it out, and then I++ at the end. Now let's go ahead and compile it and see, oops. I forgot my opening curly bracket there. There we go. And let's run it. And we can see that it is the exact same thing. It goes from sorry, it's not the exact same thing. What did I do? What did I do wrong? What did I do differently? Yeah. Okay, so let's go ahead and play around with that. If I did plus plus at the top, that's not exactly what the for loop did, because remember the for loop does it at the bottom, at the end of the loop, right? But I will get somewhat similar behavior. Let's go ahead and try it. Now it will start out at 1, right? It'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up, but 11. So we're off by 1 on the other end. So how do I fix that so that it is exactly the same behavior? Go ahead.
Well, to change the R loop down to the bottom, you have to, when you first define the variable, you have to get I equals
1. Okay, good. All right, and let's try that. And then we'll explain what we just did. Now it's exactly as before. So the key difference here is that, well, first of all, you use a different word. They're spelled and pronounced differently, right? So, right. But also those 3 elements, the initialization, the continuation, and the increment are all on different lines. This gives you a little bit more flexibility in some sense, right? For example, like the flexibility that you just pointed out, that I don't have to do my increment at the bottom of the loop, at the end of the loop. I could do my increment at the top of the loop. I could do my increment somewhere in the middle of the loop, right? Whereas a for loop is always going to occur at the end of a loop. A while loop, I can do it wherever I want, or not at all. What's going to happen here? I is 1. I is less than or equal to 10, so print it. I'm never making progress towards my termination condition of more than 10. So let's go ahead and try this and see what happens. It's still going, by the way. It's printing 1 forever. You will write code that ends up in an infinite loop like this at some point in your life. How do we stop it? Close out the browser, restart the entire computer, kill it. Literally, that's what I just did. It's called killing the program. Usually it's usually it's Control C, right? I believe that'll work on Windows. I believe it'll work on Mac. Control C, that's what this ~C is right here. It read my interrupt request, my command to kill it, right? Here's another way that you can kill it. Right? It's running in the background right now, right? Oh no, I might have painted myself into a corner here. Yeah, oh well, let's go with a new terminal. You can have multiple terminals, by the way. I think that's it. Let's find out. Let's go ahead and kill 1420. Okay, I just killed myself. I have to guess which one it is. Kill 1452, or they might not be related at all here. Okay, there we go. That was not me. That was something else entirely. Okay, so ultimately, yeah, you can go ahead and close this terminal. Yeah, don't ask me that again. And I'll go ahead and go with a completely new terminal here. Start completely fresh. Right? There we go. But if I were on, say, CSE, I could look at all my processes and I could kill those processes. And PS is to list the process. These are the process IDs. And note here, for example, I just ran PS, but of course it's already dead. If I run it again, you can see that it has a different process ID. Bash is what I'm actually using here at the command line. And so I don't know why it has two bash scripts going, but I could kill one or the other, and but then I would lose my terminal. Right? So if you're ever out in the CSE command line, you can look at all your processes and you can kill them if you want. Right? All right, so let's restore this so that it is not an infinite loop. Right? How can I manipulate this? So let me go ahead and cut and paste this over here, and let's make some observations. Right? So differences. So what's one difference? It's spelled and pronounced differently, right? The main difference is that all three elements are separated. Right? In general, a while loop is a bit more flexible. Oops, sorry. There we go. It's a bit more flexible. However, here's a truth. Right? Any for loop can be rewritten as an equivalent while loop and vice versa. Right? So when would you use one over the other? We'll get to know that later on next week. Right? But what are some other differences here? The increment this is one reason why it's a little bit more flexible, may be placed anywhere inside the loop body. Right. So you are not restricted to it executing at the end of the loop. You can do it at the beginning if you really want to. Right? Generally, the initialization occurs before the loop. Right? The continuation is still bound to the while keyword. Right? That I have the while keyword right here, and then immediately after it, I have parentheses, and inside that, that's the continuation condition. As long as that's true, the while loop will execute at least one more time. As long as the continuation condition is true, the while loop will execute at least one more time. Right? Let's see, what else? No semicolon in there, right? No semicolon in the continuation condition. Right? The loop body massacred that, the loop body is still denoted with curly brackets. And you should. And finally, the last thing that I wanted to note here about the differences are I forget. Yeah. Oh, the last one is with a while loop, you cannot scope the iterator variable to the loop itself, right? And what I mean by that is because I'm forced to declare it before the while loop here, it still exists after the while loop, and I can restore this piece of code right here and show you that in fact it does go up to 11. So GCC demo, there we go, and run it. And you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it does exist after the while loop. You cannot do something like this. First of all, it doesn't even make sense. Int I is less than or equal to 10. If I'm going to declare a variable, I need to set it to something. I would need something like I is equal to 1, and then while I is less than or equal to 0. But now we're back to square one with a for loop anyway, right? If you want to do something like that, you're shopping for a for loop, right? Don't come paying for a while loop instead, okay? All right, and then finally, I will note here, to kill a runaway program, use Control C, right? To kill it. All right, any questions? No? Well, then you'll get more exposure when you do your 4th module reading. Now we're back on schedule, so readings are again due on Monday, labs on Tuesday, hacks are assigned, you start hacks on Thursdays, and then you get them done on Monday nights, right? Everything was shifted because of Labor Day, but now everything is back to normal, right? Okay then, have a great weekend. 13.5 points.